to look at some examples on probability. All right, so what we're going to do today is we're going to determine whether an events are independent or dependent. So independent does not affect each other, dependent does. And then learn how to find the probabilities. How does that change what we do when we find the probabilities? Okay. Did I start recording? I don't either. You don't think I did? You might have. Oh, we are recording.
You're ahead of yourself as well. That's good, right?
All right. So that's what we're doing today. No, I can't remember anything. Okay, so what I did was I printed out some of the definitions for you, and then you can add what you want from the examples we look at today. So, events are independent if the occurrence of one event does not affect the probability of the other. Does that make sense? One does not affect the other. So here's an example. If a coin is tossed twice, it's landing heads up on the first toss and landing heads up on the second toss. These are independent events because tossing the coin the first time does not affect tossing the coin the second time. Does that make sense? Okay. The outcome of one toss does not affect the probability of heads on the second. So, to find the probability of tossing heads twice, we would just multiply those probabilities. And we did some of that on our homework, didn't we? Okay. So, here is the actual formula. If A and B are independent events, then the probability of A and B occurring is the probability of A times the probability of B. And I'm going to add this to my notes page also. No, I'm not. Hold on. There we go. Okay, so if we look at this, we've got some notation, and this is one of the ones I gave you on the printout. What does this U mean? Intersection. Intersection. So the probability of the intersection of A and B is the same as the probability of A times the probability of B. So let's look at this. If we took it and we solved for A, the probability of A occurring, do you see that the probability of A is the probability of the intersection divided by the probability of B? And the intersection ends up being the probability of A given B. So this is our notation, and this is what it ends up being. So the probability of A is the same as the probability of A given B if they're independent. And we'll do some examples to where that makes more sense in just a minute. What now?
What is A given B?
That, we're going to look at that in just a second. Given that B occurred. Okay. Now let's look at some examples that clearly show us independent events. A six-sided cube is labeled with the numbers 1, 2, 2, 3, 3, and 3. So we're definitely not gambling now, are we? All right. The four sides are colored red, one is colored white, and one is colored yellow. Find the probability of tossing a 2, then a 2. Okay, so we have this weird cube, and they set it up for us. It's got these numbers on it, and it's got some colored sides. Does tossing a 2 on the first toss have any effect with what's going to happen on the second toss? No. So these events are independent. And when our events are independent, we can multiply our probabilities. So what is the probability of tossing a 2 and then another 2? It's just the individual probabilities multiplied. So this would give us 1/3 times 1/3, which is 1/9. Got it?
Yeah.
Okay? Because it's independent, we just multiply the individual probabilities.
To find what?
The probability of tossing a 2 and then another 2.
Okay.
You would multiply the probabilities. All right, so now let's look at this. Same scenario, same weird number cube, same colored sides, but this time it's of tossing a red, then tossing a white, then tossing a yellow. Does tossing a red on the first one affect the second one? No, there's no relationship between the two. So these, once again, are independent. So we can do the probability of a red, then a white, then a yellow, is the probability of the red times the white times the yellow. What is the probability of a red? 4/6. And then the probability of a white is 1/6. And the probability of a yellow is 1/6. So 4/6 times 1/6 times 1/6 is 1/54. You are correct. Okay. All right, let's see if we know what we're doing. Find each probability of rolling a 6 on a number cube. Now, this is not the one we were just talking about, just a regular die. A 6 on a die and a 6 on another number cube. Do they affect each other? No. So, what is the probability of getting a 6 on the first one? 1/6. And getting a 6 on the second one? 1/6. So, what would be the overall probability? 1/36. Okay. All right. Now, this is tossing a coin. What is the probability of getting heads, and then tails? Okay? So, it's going to be the probability of heads, and then tails is 1/8. Any questions? Good. Okay, the second definition is also on your sheet. Events that are dependent events if the occurrence of one affects the probability of another. So, for this example, we're going to pretend like there are 2 lemons and 1 lime in a bag. Okay? And we're going to pull out 2 pieces of fruit. The probabilities change depending on what I pull out first, don't they? Okay, so let's see how this would look visually. If we created a tree diagram, here's our bag. And since we have 2 lemons and a lime, on our first draw, the probability of getting a lemon is 2 out of 3. But a lime is 1 out of 3. Now, oh! That was a... you heard it. Okay. Now, on the second one, we have to assume we have drawn the lemon here. So we're 1 lemon down. So now we only have 2 pieces of fruit. 1 is lemon, 1 is lime. So there's 1/2 for a lemon and 1/2 for a lime. Does that make sense? Okay, now if we drew the lime first, which we already agreed was 1/3, we have only lemons left. So what's the probability of getting a lemon? 1. And what's the probability of getting a lime? 0. So do you see how to make this tree diagram? Okay, so what we would do, the probability of a specific event can be found by multiplying the probabilities on the branches. So, the probability of drawing 2 lemons was 2/3. Y'all remember that first branch was 2/3. And then 1/2 for the second branch, which gives me 1/3. So let me go back one more time. And let's take a look at this. So, if we do lemon and lemon, it is 2/3 times 1/2, which gives me a probability of 1/3. We got it? What would be the probability of doing a lime than a lemon? 1/3 times 1. So a lime than a lemon would be 1/3. What about a lime and a lime? 0, because there aren't 2 limes in the bag, are there? But if I did 1/3 times 0, what do I get? 0. Okay, we good? All right. So what does this look like in math speak? In math speak, it looks like this. To find the probability of dependent events, you can use conditional probabilities. This is given that something has occurred. We say this, the probability of B given A. So given that A happened, this is the probability of B given that event A has occurred. So if A and B are dependent events where one does affect the other, this is what we do to find the probability of A and B. We do the probability of A times the probability of B given that A happened. Okay? No, it's not getting hard. It just looks weird.
That just happened.
All right. So what this ends up being is the intersection of the two, the probability of the intersection over the probability of the given. The probability of the intersection over the probability of the given. All right, so let's look at some problems now. So we've got our two number cubes. We got one white and one yellow. And we want to explain why we think this is a dependent situation. The white cube shows a 6, and the sum is greater than 9. Well, do you see that the second part depends on the first part? That the sum is 9. You have to use that first part to figure that out, don't you? So this is a dependent situation. Got it? So how do we do it? We find the probability of white. And then we find the probability that the sum is greater than 9 given that we have the white. And then we multiply those two. There you go.
That's what that little line thing is.
Yep.
I just wonder what that is.
The probability that it's a white 6, and then the probability that given that we got a white 6, how can we have a sum of that is greater than 9? Well, let's make sure this makes sense to us before we move on. Given that the white one is a 6, and we want a sum greater than 9, then we could have that paired with a 4, or we could have that paired with a 5, or we could have that paired with a 6. So this is 3 out of the 6 possibilities, isn't it? What's 3 out of 6? 1/2. Do you see where that comes from? Given that the first one is a white 6. So we know this is true. So that only leaves us 6 possibilities, because we're only looking at what happens to the second one. Because we know the first one is a white 6. Got it? All right. Let's move on. Okay, this one. 2 number cubes are rolled. One is white, one is yellow. And they don't have to be different colors. We could have 2 white ones. But they want you to be able to differentiate. The yellow cube shows an even number. And the sum is 5. What is the probability that that one happens? So, first of all, let's take a look. What is the probability of an even number? 1/2. Okay? Now, given that this first one is even, we are only looking at a sample space of 18, right? So, out of those 18, how many ways could we have a sum of 5? 2. So we get 1/2 and 2/18. 1/9 is 1/18. Because the 2 could be paired with a 3, and the 4 could be paired with a 1. Yes, sir.
Are we finding the probability, like, is it the probability that a yellow one would happen and then the number would happen, or is it if the probability that if the number happened, what's the probability?
You kind of have to assume, even though they can happen at the same time, you're assuming one happens first.
Right, but is it asking what's the probability the sum is greater than 9, given that the cube is showing a number greater than 4, or what is the probability that you'll get a number greater than 4 and then a sum greater than 9?
And the sum is great. It's and. Yeah,
Okay.
it's an and. But it's dependent on the first part. Okay? All right, do we want to do another one like this? No, we're good? Okay, yes, sir.
Or did you get the 1/2 times 1?
The 1/2 came from the even, the probability of even.
Okay.
So half of them are even. Okay, we'll flip through this one. I'll put this PowerPoint on my website too. So if you want to go back later on and look at some of these. All right, we can also look at additional probability when we have categorized data. So here we go. Here's a table. The table shows the domestic migration from 1995 to 2000. If a person is randomly selected, find the following probabilities. We can't see the table anymore, can we? That's kind of a bummer. That an immigrant is from the West. So, let's go back and look at the West. Okay, so how many immigrants are from the West?
2,666.
2,666 out of,
Wait, what's the difference?
2,654 out of the 11,600. Okay? So this out of, where did we get the 11,000? We totaled all the immigrants. So when we look at this, that an immigrant is from the West, we found the West, the immigrant, thank you, over the total immigrants. The ones from the West over the total. Does that make sense? Guys, this is two-way tables from last year. Do y'all remember doing this last year? Yeah. So it's the same thing. All right, that someone selected from the South region is an immigrant. So if we go back, South region is an immigrant. So we would do
5,042 over the total.
Yep. Okay? And let's put the answers up here so you can see. 5,042 over that total. Okay. We don't need to do all these. Okay, here's my favorite. We like cars. Now, look at that top part. Events are independent when there is replacement. Events are dependent when there is not replacement. So, independent events if there is replacement, dependent events if there is not replacement. So when you're reading through your homework problems, that's a key thing to look for. Am I putting stuff back? Does it affect the next thing? If there is no replacement, then that gives us a heads up that this is a dependent situation. Okay, do you feel like you've seen enough? We're good? All right, we'll take out your book and let's work on these problems.
Can I do the homework on the back of this sheet?
You sure can.
Saving a tree.
Saving a tree.
A whole tree.